Welcome to the session 7 of ITCS. So my name is Adam Bouland, and I'll be giving the traditional chair rant to kick this session off. So I was trying to think of a title for this session, and I decided that the title should be "It's the Complexity Session." This session contains a number of innovative new models of complexity, some trade-offs and boundaries with well-established complexity problems, some new contributions to mathematical foundations, and a few super polynomial lower bounds as well. So it's kind of everything you would want from a complexity session. Purely coincidental letter choices, of course. So the first talk will be a talk on lower bounds for non-monotone comparator circuits by Robert Robere and Anna Gall. And here the kind of starting point of this talk is that proving circuit lower bounds is very difficult. So a lot of our progress in proving circuit lower bounds has been in restricted models of computation like branching programs or span programs. And what they'll be presenting is the first superlinear lower bound on a model known as comparator circuits, which they argue has some power that is in some sense between branching programs and general Boolean circuits. All right. The second talk will be a talk on signed tropical convexity by Georg Loho and László Végh. And here they'll be talking about something called tropical numbers. And they're basically like the real numbers, but where plus is replaced by a min and times is replaced by a plus. So it's a slightly different number system than what you're used to. And in this work, they rigorously define a notion called tropical convexity. And the motivation here is, maybe new algorithms could emerge by thinking about this notion of convexity. And they also kind of discuss the complexity of certain kind of linear programming-like problems in this setting that end up having different complexities than the real numbers. Some of them end up being NP-complete, some of them are an NP intersect co-NP, but there's kind of a rich complexity in mathematical theory to describe about tropical convexity. It would appear that someone's calling me. Okay. Hi, Mom. Okay. So the next talk will be about approaching the min circuit size problem from above and below by Rahul Ilango. And this is a really interesting talk because the min circuit size problem is this well-known problem that's in NP, but we don't have polytime algorithms for it, nor do we have a proof that it's NP hard either. So it's in this kind of weird intermediate land of complexity. And this work kind of provides two results. First, they show that some oracle variant of MCSP is NP-complete. So they call this approaching MCSP from above because they're kind of defining a more powerful model of circuits and then trying to study the complexity in this model. And they also consider the power of restricted forms of MCSP, namely AC0D circuits. And you can see these results as kind of approaching MCSP from below because they're studying more restricted classes of circuits and what does MCSP look like in this model. The fourth talk will be a talk on trade-offs between size and degree in polynomial calculus by Lagarde, Nordstrom, Sokolov, and Swernofsky. And this will be a proof complexity talk about something called polynomial calculus resolution proofs. Usually in this setting of proof complexity, you're trying to prove that something like a KCNF is unsatisfiable. And the results that they present are kind of some trade-offs between the size and the degree of proofs in this proof system. So their kind of headline result is something like if you allow, for any sufficiently large C, if you have really high degree refutations, they can't have really short proofs. Degree C refutations can kind of be a medium size, but if you have lower degree refutations, they have to have exponential size. So there's some trade-offs here to be made between the size and degrees of these proof systems. The fifth talk will be on linear time subgraph counting, graph degeneracy, and the chasm at size 6 by Bera, Pashanasangi, and Seshadri. And they'll be talking about a particular counting problem, which is if you're given a graph G and the number K, count all of the subgraphs of G which are of size less than K. So, there's only some, for a fixed K, there's only some finite number of them. And they'll be specifically studying this on bounded degeneracy graphs. And their main result is that there's a sort of weird phase transition in hardness that occurs as you vary K for this problem. So it turns out their main result is that if K is less than 6, there's a linear time algorithm here. But if K is more than 6, then some fine-grained conjectures tell you there is no linear time algorithm. There's some weird gap here that occurs. All right, and the final talk of the session will be on the impossibility of probabilistic proofs in relativized worlds by Alessandro Chiesa and Siqi Liu. And here they're going to be initiating the study of relativized probabilistic proofs. You can think of it as asking questions like, for what oracles O is NP to the O contained in PCP to the O with some particular parameters? And this paper is interesting because it has lots of no-go results saying that for certain random choices of O, this is not possible, and kind of the fact that PCPs are not possible in some of these relativized worlds has some interesting things to say about cryptography. All right, so yeah, thanks for your attention, and let's get started with the first talk on lower bounds for non-monotone comparator circuits. Robert Robere will be giving a talk. Great. Cool.
Hopefully. Okay, good. All right, can everyone hear me all right? Great. Okay, so hi everybody. My name's Robert. I'm here to talk about this new circuit lower bound that I have with Anna. This talk is apparently being broadcast on YouTube, so hi YouTube. Okay, let's get started. So the central open problem in complexity theory is to prove lower bounds on on what we would consider relatively weak algorithms, right? So here's kind of the lower bound, which is at the very boundary of what we understand how to do right now, which is just show SAT, or any NP language at all, requires super linear size circuits, right? So throughout this talk, when I refer to a circuit, I'm going to refer to a Boolean circuit. So just in case, everyone's probably familiar with this, but just in case you're not, so a Boolean circuit is composed of and, or, and not gates. And kind of crucially, you can sort of fan out gates. Like the individual gates are allowed to sort of fan out their computations as many times as they would like. Okay, so this is a sort of a classic model studied in complexity and algorithms. It can simulate any polynomial time algorithm like efficiently. So this is sort of a good proxy for what we consider to be efficiently computable. Okay, well, what we have, unfortunately, if you want to consider proving any lower bounds at all, Boolean circuits are kind of at the boundary of what we don't understand. So if you look at weaker models of circuits, so here's a family of models that are normally considered, we can prove superlinear lower bounds, and sometimes sometimes like even better. So branching programs, for instance, are a model of like space complexity, and we can prove bounds for that. Boolean formulas model parallel computation, and constant depth circuits, famously, we have exponential lower bounds. So here's kind of a breakdown of what the current results that we have are, and you can see as the model gets stronger, the lower bounds get progressively weaker. So for constant depth circuits, we have exponential lower bounds due to Hostad, all the way back in the 80s now. So for Boolean formulas, we have cubic lower bounds, the original essentially cubic lower bounds. This is also due to Hostad back in 98 with a recent improvement in the lower order terms due to Tal. For branching programs, we start getting like weaker and weaker. We have quadratic lower bounds. And then for non-deterministic branching programs, and for our sort of somewhat related model called span programs, we have lower bounds of the form n to the 3 halves. And now you can ask, what happens with regular Boolean circuits? And it's kind of a sad fact that we only have linear lower bounds for Boolean circuits. And these linear lower bounds are even for a function that's computable in P. Like it's not even for a function computable in NP. So this is far away from what we sort of expect to be true. Does that make sense? Okay. So like Adam mentioned earlier, the main talk about today is, the main result I'm going to talk about is kind of pushing this boundary just a little tiny bit further. So we're going to describe a new model called comparator circuits. They're in between the power of non-deterministic branching programs and Boolean circuits. And we'll actually be able to prove superlinear lower bounds on the sizes of the model. Okay? So what are comparator circuits? They're a very natural model. Okay? So a comparator circuit is just a circuit that's composed of a comparator gate. So what is a comparator gate? Well, a comparator gate just takes two bits as input, A and B, and it outputs the bits in sorted order. Okay? So it takes, you can imagine it as taking like both the OR and the AND, or like the min and the max of the two input bits. Okay? And then a comparator circuit is just going to be a circuit that is only composed of comparator gates. And so at the inputs we can have, positive and negative literals sort of as usual to sort of take care of the knots. Okay? So just to get an idea of how these things operate, I mean, I'm going to usually draw comparator circuits like this. The nice thing about the comparator gates is that since they all have two inputs and two outputs, you can kind of imagine the wires, like the number of like wires is never going to change throughout the computation of the whole circuit. So I'm always going to draw it like this. The inputs will be labeled on these wires right here. And then for every gate, I'll just take the two input wires and leave them to the two output wires. And now the circle will correspond to the and the arrow will correspond to the or. You can kind of think of as the one as being pushed towards the arrow. If that makes sense. So this is going to sort these input bits in increasing order. The or is on the bottom and the and is on the top. Okay? So proceeding, we can see at this next gate, okay, we have a 1 and 0. So again, it's going to sort, right? Now the next gate is being applied to the top and the bottom wire. It's 0, 0. So there will be no effect, and then no effect again, no effect again. And then, we'll just designate one of these outputs to be like the output wire. Does that make sense? So there's two natural complexity measures that could be associated here, the number of wires and the number of gates. So just to make it totally clear, this circuit has 4 wires, as you can see. The wires correspond to like the number of inputs that are being read, and it has 5 comparator gates. And I'd like to remark that like I can always label multiple wires with like the same input. Like these circuits are like they can't necessarily make copies of a single input variable. We'll talk about that a little bit more in a bit. But okay. So if we understand what the model is, okay, well, why are these things interesting? Well, one natural answer to that is that a special case of these things are sorting networks, which are a model that have been studied to death in theoretical computer science, okay? And this is just a model where you're given n distinct inputs, and the goal is to sort the inputs in increasing order at all the outputs, okay? And this is like the right model for oblivious sorting algorithms, like algorithms where the comparison steps don't depend on the actual data that you're looking at. Like the same order of comparisons are always going to are always going to happen in the same order. So there's this famous result due to Kolmos and Semiretti from the 80s that says, in fact, you can implement a sorting network, something that sorts all the input bits using only order n log n gates of hardware, right? And in this case, a sorting network sort of corresponds to like a read once circuit because every input bit is read at exactly one input wire, right? And so what a comparator circuit is it's like the generalization of that where now we want to compute any Boolean function. And you can have, this allows that we can allow negations on the inputs, and we can also allow multiple copies of the same input bit. So if I let CC denote the class of languages that's computable by polynomial size comparator circuits, it turns out to be quite a nice class. So it contains NL, so non-deterministic log space. It's contained in P because clearly any circuit can be, any Boolean circuit can simulate one of these things. And what's interesting is that it's conjectured to be incomparable to NC. So if you're familiar with the complexity classes inside P, this should come off as a little bit weird because there's not very many classes which are like orthogonal to NC, but contained in P. And there's actually a very natural complete problem for this class of circuits, and this is the stable marriage problem. So all in all, I think this thing has been relatively understudied. In fact, there's only 2 canonical papers studying this thing, and it's these 2 papers by Subramanian who introduced this paper and a recent paper by Cook, Filmus, and Lee, which kind of revived it. Yeah. Okay, so what's known about lower bounds? Well, from the sorting networks, apparently we have basically matching lower bounds for sorting networks. A counting argument, just like the normal things that we're used to, gives exponential lower bounds, but for like a non-explicit function. And for monotone comparator circuits, turns out we have basically all the lower bounds we would like. But for the regular model, the standard model of non-monotone comparator circuits, like absolutely nothing is known. So the read once lower bound for sorting, I mean, this only, like in some sense this is less interesting because it's one thing, it's computing a function, it's like a multiple output function instead of a single Boolean function. And for the second thing, I'm only allowed to read each input once. So it's kind of like a restricted model. Okay? So the main result for today is actually a superlinear lower bounds on these things. So here's the function for which we prove the lower bound. It's the element distinctness function. Okay? So what is it? Well, it's pretty simple. You're given m integers in the range 1 to m squared, and you want to decide if all the integers that you were given are distinct. And this can be encoded by a string of roughly m log n bits. Right? And the main theorem is that any comparator circuit for this function is going to need n to the 3 halves wires in order to compute it correctly. So remember, by wires, I really mean like the number of times a variable is being read at the input here. So this is stronger than like a gate lower bound. We're actually proving something like, in principle, you could have like, you know, a small number of wires and much more gates. So this is, our lower bound is actually on the number of reads, which is sort of a strength of this result. For this function?
Yeah, repeat the question, please.
Yeah, so the question was, if I got it correctly, is like, what's known for this function for arbitrary circuits? And the answer is there's no lower bounds. I mean, there's a linear upper bound, order n. Yeah, so. Okay. So how do we prove this lower bound? Well, the answer is that we're going to use sort of we're going to recruit a classical technique, except in some sense, it provably can't work. So that's kind of, I guess, what's innovative about this paper. So what is the Nitschke-Pork method? Well, the main observation is just the following. If I have a circuit for a function, it's also going to give me a circuit for any restriction of the function. So if I plug in a bit right here, it'll simplify. Like if I plug in a value for x1, I can simplify the circuit and get a new circuit for the subfunction obtained by this restriction. Right? So the Nitschke-Pork method for formulas proceeds as follows. We're going to choose a partition of the inputs. We'll take the set of leaves, which correspond to the variables, and then the size of the formula will just be the subset of these guys right here. And the main thing that we're going to do is we're going to bound we're going to sort of compare the number of subfunctions that you can obtain by restricting the function to the number of formulas that you get on this restricted set of leaves. And with this element distinctness function, it turns out we can get, a lower bound on the number of distinct functions you can get by restrictions. And the number of formulas on W of I leaves is clearly pretty good. It's like 2 to the order of W of I. So if we wanted to do this thing for comparator circuits, here's the whole plan, just plugged in with comparator circuits instead. Now, the problem is that we have to bound the number of comparator circuits with W of I wires. And now this is a problem because the gates can fan out, right? Like in principle, I can just keep adding gates forever. So if you fix the number of wires, a priori, there's no bound on the number of gates, right? Like the number of comparator circuits with W wires should depend both on the number of gates and the number of wires. And this is really bad for us because it means that like this lower bound technique just simply cannot work, right? Except it turns out that this claim is totally false. And in fact, this will work. So the main theorem that we prove along the way to these things is that any comparator circuit with W wires actually has at most W squared gates. In fact, W choose 2 gates without loss of generality. So you can't just keep repeating gates forever. Eventually, if the circuit is minimal, some of those gates are going to be useless, and I can throw them out. It turns out this is tight due to due to the bubble sort algorithm, basically. And the intuition for proving this thing is basically that comparator gates cannot copy, and I'd be happy to explain this a bit more offline. So with that, we can kind of bound the number of comparator circuits on W of I leaves, which allows us to sort of plug this into the Nitschke-Pork method, and then we can sort of follow the normal strategy and then prove the bound. Okay, so I guess that's all my time. So we proved the first superlinear lower bounds for comparator circuits. Obviously, there's a limitation here in that the lower bound only goes up to n to the 3 halves. A natural question is whether or not we can prove quadratic lower bounds or better. And I'd like to point out that the usual lower bound techniques for circuits that get even the linear lower bounds really don't work here for proving lower bounds on the number of wires. So random restrictions cannot work in a black box way. So is there a way to lower bound the number of gates directly? And also, it's natural to ask if there's something special about the Necheporek method that allows it to prove these lower bounds for these restricted models. And yeah, that's it. Thanks.
Any questions? Yeah, so I'll have a question while the next speaker sets up. So is there a reason to think that quadratic is the best you could get here? Is that an obvious?
So for formulas, by applying this method, you can actually get quadratic lower bounds. So it's a little bit weird that there's a gap that happens here. So that's kind of the natural reason to suggest it. Yeah.
Convexity by Georg Loho. Go ahead.
Thank you. So this is based on joint work with László Végh. So at first I want to correct a bit. So it's not min plus. Well, it's not really a correction because you can actually do min plus or max plus. This is essentially the same. And so the whole idea is we want to replace sum by max and multiplication by plus. Okay, so this is kind of the setting, and we can do a lot of math just by replacing these operations, and I will show you soon why you should do this or why this can help. So in particular, if we apply this to linear programming, then let's look at this inequality. So we can just think this is a usual linear inequality where we replaced the summation by max and the multiplication by plus. And well, it's a bit weird maybe because we have these variables on both sides and we are used to having only variables on one side maybe if we have a linear inequality system. But this just comes from the fact that there are no additive inverses. Makes sense because there are, like if we have max as operation, there are no inverses to this operation, this binary operation. And it turns out the problem, the feasibility problem for systems of this kind are an NP intersected co-NP, and there is no polynomial time algorithm known. So essentially this problem goes back to Guvic, Karsanov, and Kachian in 1988, where they defined this as mean payoff games. I will explain this in a second. And then it occurred under the name of and/or scheduling, and finally as tropical linear programming. So really this tropical means these operations max and plus. So, but as I said, there are no additive inverses, which is, well, a bit undesirable in many ways. And so we tried to get rid of this restriction, and well, the most natural form without any other operations you can see is this, where we allow to swap numbers, which essentially amounts to multiplying with minus if we would do this with the usual operations. But I will show you a calculus in which we can just write it in a compact form. We are kind of used to this then, and we just have this weird symbol which is something like smaller or equal to, but well. And it turns out if we go to this more general setting, suddenly this linear programming type problem becomes NP complete. So but what is the motivation? So I have a lot of motivation for you. So as I already mentioned, tropical linear programming is equivalent to mean payoff games. They are widely studied in theoretical computer science, in particular because they are known to be an NP intersected co-NP, but there's no polynomial time algorithm known. This is a very interesting complexity status, and the so-called parity games form a subclass. And these parity games were shown to be quasi-polynomial time solvable in a paper by Kalut, Jain, Kusainov, Lee, and Stefan in Stock 2017. Also, there's a connection with classical linear programming, and in particular, this connects to the quest for a strongly polynomial time algorithm for linear programming. So this connection was drawn in a series of papers from 2015 on. In particular, we get a connection for some strongly polynomial algorithms for linear programming. We get strongly polynomial algorithm for mean payoff games, and one could show that certain log barrier interior point methods for linear programming can't be strongly polynomial, because one could show with these tropical methods a dependence on the coefficients. And one can also model scheduling problems. I already mentioned this, like and/or scheduling. So, as I said, this has a modeling power. This has some connections to problems, complexity questions. But we had there was this weird problem that we had this restriction of non-negativity inherently in these operations. Therefore, we used a framework from 1990, which was called symmetrized tropical semiring, to get rid of this restriction. So the idea is, like, how would we construct the integers from natural numbers? Well, we double the numbers and define some rules, what cancellation means. We can try the same here, so we just double the real numbers. The 0 is minus infinity, and we get so-called negative tropical numbers, but it turns out there can't be additive inverses, so something weird has to happen. So we have to introduce a third copy, which are called balanced numbers, and which is essentially a blown up 0. And then we get operations which extend max operation and the plus operation. And how does this work? Just a little intuition. So like 4 plus 4 is again 4 because it's just max. So the weird thing just happens if we try to add these positive and negative numbers, because then we get a weird cancellation, namely we get a balanced 4. But essentially, otherwise, it's again max, so 4 plus minus 5, really the value wins, the 5 wins, so it's minus 5. Okay, I don't want to go into detail, I just want to give you a little intuition. So one can try to model this, but stuff goes just wrong. In particular, we also, as I said, we want to define inequalities, but also this doesn't work well. One really doesn't get an order relation, one doesn't get an equivalence relation replacing equality. So one, as you can see in the example, we get this relation which is really not transitive. So what could we hope for? Surprisingly, it works well to some extent. So we can define a convex hull in this setting with these signed tropical numbers. And well, you can see such a weird shape here. This is just a signed tropical polytope. And if you look at the definition, well, we just replaced the equality with this weird balance symbol. And otherwise, can just think of, we replace the sum by the tropical sum and the multiplication by the tropical multiplication. And suddenly we get a geometric object which one can study and which has very desirable properties for a convex hull. Namely, intersection preserves convexity, and projection preserves convexity. It's a Hull operator, and we have this usual aspect that essentially the convex hull is defined by taking line segments. But also we get weird phenomena. For example, the left one is a line segment, but it's two-dimensional. So, okay, it's a bit unexpected, but it in particular fulfills one very desirable property. So we're actually interested in tropical linear programming, and so we wanted to have some duality between this convex hull and the separation, and this is what we really get. So you see these 3 red points, and in particular you can see that these 3 red points are separated from the origin by such a crooked hyperplane, but it's an open half space because now we really saw why these tropical things are harder, why really tropical linear programming, even if it's an NP intersected co-NP, is so far harder to deal with than classical linear programming. Namely, we can define open affine half spaces, like signed tropical, but okay, like open half spaces by this just a strict inequality, then closed half spaces by this replacement of a non-strict inequality with a property that the non-strict inequality gives really the topological closure. And now really something very unexpected happened. So open tropical half spaces are convex. Okay, that's why separation works. But closed tropical half spaces are not convex. And this really gives rise to this distinction between NP intersected co-NP and NP complete. So this first formulation is just the same problem as I showed you in the beginning with the max and plus inequalities, just where we replaced the inequality symbol with this new inequality symbol. And this is an NP intersected co-NP, but suddenly if we drop this non-negativity condition, then we get an NP complete problem. Namely, this is just actually a geometric version of the SAT. As one can see, as these, the addition is essentially a generalization of OR, and the negation is really just essentially the negation in a formula. Also surprisingly, many other geometric constructions work. So for example, Fourier-Motzkin elimination, which is at the heart of the proof for the separation. I mean, it's an elimination, so actually variables should cancel, but there is actually no cancellation, but it works nevertheless. And also a Minkowski-Weil type theorem can be shown. So what we really like about polytopes, so we have an inner description and outer description. This works even if closed half spaces are actually not convex. Then we also exhibited several relations with other existing concepts, which I don't want to get into detail to. And with this, I want to conclude. So we exhibited this new structure which extends the existing tropical convexity. So there was a tropical convexity without signs, but in this way, with this extended version with signs, we can model more geometrically several complexity problems at the intersection of NP intersected co-NP going to NP completeness.
Okay, so let's thank our speaker. Any questions? All right, let's thank the speaker again. Approximating MCSPs from above and below.
All right, great. So if you ask a physicist when time and space begins, they'll probably tell you about 14 billion years ago in the Big Bang, but they're wrong, because time and space actually began in 1965 when Hardness and Stearns published the first results on time and space complexity classes. And you might think the story begins there, at least the story of complexity theory, but interestingly enough, 6 years before, a Russian mathematician, Yablonsky, started studying a computational problem that we now call the minimum circuit size problem, and he was trying to show that the problem was intractable. So what is the minimum circuit size problem? Well, minimum circuit size problem, or MCSP, takes two inputs. The first is the truth table T of a Boolean function, so just all the values the function takes on all of its inputs. And the second is just a size threshold, S, which is a natural number. And the output of MCSP is, does there exist a circuit with at most S wires computing the function F? Is it clear? Anybody have any questions? All right, great. So some facts about the complexity of MCSP. First, MCSP is actually in NP, and you can basically just use a minimum size circuit for the function as a witness to yes instances. And it's also probably not in P. And the reason is, if it was in P, then we wouldn't have cryptography as we know it. And so the natural question is MCSP NP complete? And this is a big open question, and this is what we're partially investigating in this work. So I've told you what MCSP is, but why should you care about MCSP? And while you may not care about MCSP yet, you probably care a lot about another problem, SAT. And why do we care about SAT so much? Well, by studying SAT, we learned so much about theoretical computer science. It led to theory of NP-completeness, PCPs, SAT solvers, practically useful SAT solvers, and like a theory of fine-grained complexity. And I think that makes it clear that the problem of SAT is fundamental in that natural questions about the complexity of SAT led to important, often unexpected advances in computer science. Which leads to the question, are there other fundamental problems, and can we find them? If we had a problem that was even like half as fundamental as SAT, it would be a big deal, which makes the following claim pretty audacious. MCSP is more fundamental than SAT. What daring researcher would make such a blasphemous claim? Well, if you missed it, Rahul is my name. This is not me, Rahul. This is Rahul Santhanam, who will be talking tomorrow. And I know what you're all thinking. Why are all these Rahuls thinking MCSP is so fundamental? And I'm glad you asked. And it's primarily the deep connections this problem has. It has connections to pseudorandomness in cryptography, has connections to computational learning theory, and what I'm going to focus on in this slide, connections to circuit lower bounds and complexity class separations. Moreover, we know very little about this problem. Is it NP-complete? We don't know. Is it hard to approximate? We don't know. Can you beat the naive brute force algorithm? Again, we don't know. What we do know is that answers to each of these three questions have important ramifications on circuit lower bounds and complexity class separations. In fact, we have theorems of the following form. If something is true about MCSP, that implies a solution to a long-standing open problem about circuit lower bounds and complexity class separations. For example, if the problem is NP-complete, that would mean a breakthrough complexity class separation. If an approximation to MCSP is NP-complete, then amazingly, computing NP on average, for a certain definition of average, is as hard as computing NP in the worst case. Finally, if you could show that there do not exist circuits that compute a version of MCSP that are just barely superlinear, then you'd have that all of NP doesn't have polynomial-sized circuits. Now, the question that I'm interested in is, is MCSP NP-complete? And in some sense, this is a really old question, because when Levin himself discovered his version of the theory of NP-completeness, he actually delayed publishing his results in hopes of showing that MCSP was also NP-complete. And 15 years later, this remains, pardon the pun, a complete mystery. In light of the fact that we we haven't really been able to understand the complexity of MCSP, a natural strategy has been to try and approach MCSP from below. That is, try and prove hardness for restricted classes of circuits that we understand better. And there's been some success here. A long line of work has shown that DNF's MCSP is hard to approximate, and recently it's been extended to the depth 3 case of DNF XOR circuits. What I want to focus on in this talk is actually an approach from above, which doesn't really seem to make sense at first, but here's what I mean. I'm going to find a new problem that I call the minimum oracle circuit size problem, or MOCSP. And this problem is going to be very similar to MCSP. It's going to take 3 inputs. First is still a truth table of a Boolean function, and also it's going to take a size threshold, but it's also going to take the truth table of an oracle Boolean function O. And the output of the function is going to be, does there exist a circuit with at most S wires computing F, where that circuit is also allowed to have gates computing the oracle function O. And what's cool about MOCSP is, first of all, it's at least as hard as MCSP because you can just provide a useless oracle, but also it's still an NP since you can use the oracle circuit, minimum oracle circuit as a witness. And what this means is it provides a really useful, potentially useful testing ground for conjectures we have about the hardness of MCSP. And so the most natural question, is, can we do for MOCSP what we can't do for MCSP? That is, can we prove hardness? And unfortunately, there's some bad news here. using essentially the same techniques that of a paper of Murray and Williams from 2015, you can show that if you proved MOCSP as NP-hard, then you have a breakthrough complexity class separation, which, doesn't mean that it's not NP-hard, but it means it would be really difficult to show. But fortunately, when I say that MOCSP is NP-hard, this is NP-hard under the standard notion of NP-hardness reductions, in particular, a deterministic reduction. And in our main theorem, we show that MOCSP is actually NP-hard under randomized reductions. And what does this mean in terms of MCSP? Well, it seems like a very strange result, because it's saying, if you make this class of circuits more powerful, so something we even understand even less than general circuits, we can prove that this problem is NP-hard. And on the other hand, if we look at really restricted circuits, we can also prove it's really hard, but there's the general circuit seems to be elusive. It also suggests that maybe randomized reductions could be really useful in analyzing the complexity of MCSP, and it gives some hints as to some things that we could, that if we understood for MCSP, would yield NP-hardness reduction. It also clarifies some of the technical barriers we thought existed for proving hardness, but I won't go into this so much. So I want to just give you like a flavor of what this reduction looks like, and the heart of the reduction is really simple. And the reduction is from set cover, and so I just want to illustrate it kind of on a small example. So let's say we have like a universe of 4 elements, and we have some sets here. So the first set contains 1 and 3, and so on. So we need to map this into a function, and we need to map this into an oracle. And so for our function, we're just going to choose a uniformly random function from the ground set to 0, 1. And to build our oracle, we're going to build that oracle out of some functions that are induced by the sets in the following way. I'm going to say the function induced by the set S1 is going to be a function that is equal to the original function f, with the exception that on all the elements that are not in the set S1, I'm going to make the value of this function 0. And similarly for S2 and S3. Is it clear? Cool. And what's nice about these induced functions is that they have the following nice property. If you look at a set cover on the left-hand side, so for example S2 and S3, and you OR together the corresponding functions on the right-hand side, you actually recover the function f. So this lets you go from a set cover on the left-hand side to kind of a function computing f on the right-hand side. So if we let our oracle just be the concatenation of these induced functions, we know that f will have an O oracle circuit that is kind of proportional to the set cover instance. Now, you also have to argue about the lower bound, which I won't describe here, but is kind of really interesting. In order to make the lower bound work, you actually can't use the original set cover instance. In some sense, you have to lift it up into a higher set cover instance and randomize that instance, and that will allow you to prove the lower bound. All right, finally, I want to end with some open questions. I actually think the biggest question is hardness of approximation here. Because the reduction is coming from set cover, you get a really weak hardness of approximation, only like a log n factor, which seems to me to be like completely wrong. You should be able to prove that this problem is really, really hard. But I've thought about it, but I think it's a really interesting question. Another thing is like continuing the approach from above. I think that the hardness of this problem has shed a lot of light on like what the hardness for MCSP should look like or could look like. And there are actually, if you could try and investigate other problems above MCSP, that would be very interesting. Thanks.
Great. Any questions for the speaker? All right, cool. If not, let's thank the speaker again. All right, for our next talk, we'll have Joseph Swernofsky telling us about trade-offs between size and degree in polynomial calculus.
I'm Joseph. This is joint work with Guillaume Lagarde, Jakob Nordstrom, and Dmitry Sokolov. And when we started this work, we were all at KTH, but since then, the rest of them have fled to the remaining corners of Europe. So I'm the only one left at KTH. So to understand this, you're going to need to know about polynomial calculus. So for those of you who don't know, polynomial calculus is a proof system. So you start with some axioms and you derive a result. Often you start with contradictory axioms and you derive contradiction. So here we start at the top with these axioms like y z bar. When you see a variable with a bar on it, that's a formal new variable that represents the negation of a regular variable. So in this proof system, all the lines are polynomials. A polynomial is supposed to evaluate to 0 under some assignment, or under maybe a secret assignment. And so that means when you have a product of two things, because the product should evaluate to 0, one of the two things should evaluate to 0. So that is capturing the same behavior as an OR. That's how this is going to do logical operations. And we don't need these formal negated variables. You could have just had like 1 minus, instead of z bar, you could have 1 minus z. But by adding them, we make the system a little bit more powerful, a little bit more efficient at some things. And this is technically called polynomial calculus resolution, not polynomial calculus. So how do you actually derive new lines in this proof system? Well, if something evaluates to 0, you can perform like what you would intuitively expect to that polynomial. So if y z bar evaluates to 0, then if you multiply it by something, it'll still evaluate to 0. And if two things evaluate to 0, you can just add them. They still evaluate to 0. And then lastly, we have one equation here, this z plus z bar minus 1, that wasn't given to us and we didn't derive the normal way. So we have a few axioms that are always present in this proof system that help it to represent Boolean variables. Okay, so these proof systems are usually used to like show a certificate that you've refuted a SAT instance or something like that. And we want them, if you want to produce that certificate, you want them to be, you want to have a small proof or a small refutation. Two measures of the complexity of a refutation are their size and their degree. And that's what this result is about. So here the size is the number of monomials present in the whole refutation. And you can count them, but there are 13 of them. And the degree is the size of the largest monomial, which is the number of variables in it. So here, like x, y, z is one of these degree 3 monomials. And the reason we care about these measures are, well, one, the size is going to be roughly the runtime if you try to implement this using like the Grosvenor basis algorithm. And the degree is also going to give you a bound on size and hence the runtime. So if you have degree d, then you can refute. You only need size like n to the d for your whole refutation. So a classic result shows that if you have a reasonable size, you can also get a somewhat lower degree. So Impagliazzo, Pudlak, and Segal in 1999, they proved that when your formula has some size s, if s is like reasonably small, then you have a contradictory formula, so a bunch of incompatible, you have a set of incompatible axioms. Then you can refute those axioms in about square root of n degree. And this is the exact formula for what you can do. If you didn't have this theorem, you would naively just know that you can always refute things in degree n. You never need to I mean, you never need like multiple copies of a variable in a monomial. So this is some significant improvement. But this theorem, the way it goes is it starts with a refutation pi, and it builds a refutation pi prime, which has this low degree, but it may be extremely large. It may be exponential in size. So a natural question is like, is that necessary? And similar theorems have been shown in other proof systems, and it's shown to be necessary. But here we, in the PCR proof system, we show, yes, it is also necessary. So our result is that we consider a formula, phi. It has a refutation that's almost linear in degree, and it's polynomial in size. So polynomial is very small for size. And so by this theorem, it should have a even lower degree refutation. But even if you try to like squeeze the degree down a little bit by some additive like log n variables or additive log n degree, the size will explode to be exponential. And just as a side note, phi doesn't just have like square root of n degree refutations, but it has refutations of this very small, like n to the epsilon degree. And also, so this may look familiar to you if you work in this area. This is like exactly what Tappan proves. Tappan in 2016 proved this result, but in the resolution proof system. So this is, to get this to work, we needed to like paste on the R operator machinery and get that to work in polynomial calculus. So how do we do it? So yeah, as I said, we do everything Tappan did as a start. And then we need to add this R operator machinery. And the R operator is a technique developed by Aleknovich and Razborov, which I'll get into more in a moment. But it isn't just plug and play. In order to get it to work, it's one of the only techniques for showing lower bounds in polynomial calculus. But in order to get it to work, you need to think carefully about some of the stuff involved in it. And we tried a lot of things that didn't work, and eventually a simple trick made it work. So I'll show you the simple trick. So what is phi? What is our formula? It's a formula describing a grid. And on that grid, at every point, we have a bunch of colors, which are here numbers, because I guess this formula has synesthesia or something. So there's a formal variable for every color at every vertex. Then there are some more variables for some edges. So there's a graph on this grid. And here I've drawn dotted lines to represent like variables that exist but are set to false, and a solid line to represent a variable that exists and is set to true. So not all edges, not all like possible edges are even have variables for them. And then we have a couple of rules for this grid. So one is that out of every vertex, some arrow should be set to true. And then along an edge, along an arrow that is set to true, if there are some colors at the head of the arrow, then those colors should be present at the tail of the arrow. So here from V to W, 2 is present at W, it should also be present at V. And that's strange, you may say, because from U to V, that rule is broken. So this is the small trick I mentioned. There's a special color, which we use 0 to represent, where you don't have to satisfy that rule. Yeah, so that's the formula. Actually, this formula, as I've described, is satisfiable. So we should have something unsatisfiable. And to do that, we just add some rules that at the bottom layer, there's a color at every vertex. In the upper left-hand corner, there's no color. And so you can think like there must be a path going from the top to the top left corner to the bottom, and that path is going to show that this formula has a contradiction. So this is all pretty much Tappan except for the special color. So now we need to attach this R operator. And the R operator is an example of sort of a more general phenomenon or strategy in proof complexity, which is you come up with some measure of complexity. You show that that measure is small on your axioms, in this case 0. And by the time you get to the conclusion, it's not so small. Or the contradiction, it's not so small. And 1 is contradiction in this proof system. So R of 1 is not 0. And if you stay inside simple formulas along the way, then you can never stop having this small value. So it's always 0 as long as the terms along the way are what we call beautiful. I don't know why we call it that. You have to ask Jakob. Specifically, how do we define R? Well, R is going to be, it's going to take the polynomial, it's going to reduce by some ideal, and the ideal contains all the axioms for certain relevant vertices for this term. And the relevant vertices, I will tell you in a moment what they are. A vertex obviously is relevant to a term. Here we have a term. It looks complicated, but it's just 3 variables multiplied together. So this G variable, this F, and this H. Each variable is either a color at a vertex or an arrow at a vertex. So each variable has an obvious relevant vertex. So we should quotient by those relevant axioms at those vertices. And I'll just skip this because we don't have a lot of time. But we also need to quotient by some extra vertices to make things work because we have an expander graph. If a vertex is bottlenecked and all its edges go through touched vertices, then we also need to quotient by its axioms. So here are some extra vertices that are bottlenecked. And that's pretty much it. So it'd be cool to see trade-off results for some other systems. And yeah, that's it.
All right, any questions? So if you go back to your last slide.
This one.
Oh, no, sorry, in your open question. So do you think that trade-offs would be harder to prove for, say, sum of squares or kind of proof systems? Yeah, substantially
much harder, yeah.
Because they're more universal effect or something.
Yeah.
Okay.
Okay.
All right, great. Let's thank the speaker. By Noujan Pashanasangi on linear time subgraph counting, graph degeneracy, and the chasm at psi 6.
Thank you. Hi everyone, I'm Noujan. This is joint work with Suman Bera, who is in the audience, and Seshadri. So let's start with the subgraph counting problem. So in this problem, we have a small subgraph pattern which we call H. It could be for example, the 4 cycle. And as input, we have a large graph G with m vertices and m edges. And our goal is to count all copies of H in G. And when we say copies, we mean non-induced, meaning that we want a subset of edges in G that exactly match H. So a popular version of subgraph counting that on which there has been a lot of work both in practice and theory is counting all connected k-vertex subgraphs. For example, for k equal to 3, we basically have the triangle counting problem. For k equal to 4, we have to count these 6 patterns from 3-path to 4-click. And to give you an idea, you can also see all the patterns for k equal to 5. So subgraph counting, and specifically k-vertex subgraph counting, has been exploited in diverse areas such as bioinformatics, social networks, and so on. And in most of these areas, the graphs that we work on are sparse graphs, and specifically low degeneracy graphs. So what is degeneracy? Degeneracy is a sparsity measure. You can think of it as the maximum average vertex degree of any subgraph of G. So intuitively, if a graph has low degeneracy, both itself and all its subgraphs are sparse. if you're familiar with these terms, it is the same as k-core number, coloring number, and is very closely related to the arboricity of the graph. Here we specifically work with bounded degeneracy graphs, which is a rich class of sparse graphs. For example, it includes all minor free families and preferential attachment graphs. So first, we need to get familiar with the vertex ordering and degeneracy ordering idea, which is a central idea in subgraph counting. So the idea is just pick any ordering of the vertices, and then you can orient edges with respect to this ordering. So if U comes before V, orient the edge from U to V. And the corresponding directed graph that you get is a cycloid graph, so it's that. And now we can define degeneracy formally. So it is the smallest k such that there exists a vertex ordering that in the corresponding directed graph, the out degree of each vertex is at most k. Now to degeneracy ordering. This degeneracy ordering could be obtained by repeatedly removing a minimum degree vertex, and there is a linear time algorithm by Matula and Végh for finding this ordering. And in the corresponding directed graph of degeneracy ordering, the out degree is at most alpha, which is the degeneracy. So back to subgraph counting. Chiba and Nishizaki, in their seminal work in 1985, they gave an M alpha algorithm for counting triangles, which is basically the same as 3-vertex subgraph counting. So here I'll explain an algorithm which is more related to our technique, but is similar to theirs. So the idea is to count triangles in G arrow instead of G in the directed graph. So since our directed graph is cyclic, there is no cyclic triangle. So we count the only cyclic orientation of a triangle. And the idea is there are M edges we can map to UV. For the red edge, there are only alpha edges which we can map to because out degree of U is at most alpha. And for the blue vertex, we can just check if it's there or not. So notice that here we actually enumerated all triangles, not only counted. But as we go to 4, it's more challenging because now we cannot enumerate all 4 vertex patterns. For example, consider 4 cycle. There could be n squared many 4 cycles in graphs with, say, 2n edges. For example, the complete bipartite graph with 2 vertices on one side and other vertices on the other side. But again, what we do is that we look at all cyclic orientations of 4 cycle, and this is more challenging. I'm not going to go to the idea, but go to the details of the algorithm, but we can also do this. And Chiba and Nishizaki implicitly also gave algorithms for 4 cycle subgraph counting. So in this work, we show that 5 cycle subgraph counting could be solved in M alpha cube. 5 is also even more challenging than 4 because the patterns are larger, so you cannot enumerate much, so you have to find clever ways to actually count the patterns. So looking at this trend, M alpha squared, M alpha cube, one would expect that this goes on for size 6 and larger, but we realize that there is actually a stop at size 5, and there's no linear time algorithm for size 6. So put our problem statement as the following. So assume bounded degeneracy. We ask for what values of k vertex subgraph counting is linear time solvable, is solvable linear time. And our results have 2 parts. First part, as I said, for k less than or equal to 5, we show that it is solvable linear time. And for k greater than 5, we show that it's not solvable linear time, assuming a conjecture in fine-grained complexity, specifically that triangle counting requires omega of m time in expectation. So these 2 together gives us this gap at size 6, this jump at size 6 for k vertex subgraph counting in bounded degeneracy. So first part of our result, I just here give you the main ideas of the algorithm. So again, we want to count copies of H in G, and first thing we do is that we instead count copies of all cyclic orientations of H in G arrow, and for count like fixed one cyclic orientations, to count copies of that, we first find a directed rooted tree in H arrow, and we show that we can enumerate all copies of this tree in G arrow, and we show that this tree is large enough so that the remaining vertices and edges in H arrow we could use their structure to somehow count the ways to extend a copy of a tree to a copy of H arrow. So this way we can count actually copies of H arrow. Second part of our result, which is the conditional lower bound. So it's actually conditioned on the triangle detection conjecture, which states that triangle detection requires omega of m time in expectation. This was first introduced by Abboud and Williams in 2014. In their work, they proved lower bounds for the dynamic version of many well-known graph problems. So best algorithms that we do have actually for triangle detection needs minimum of n squared and m to the 4 by 3 and are based on fast matrix multiplication. So if triangle detections need omega of m time, triangle counting also needs omega of m time. So, and we use the triangle counting. So to sum up, assuming triangle detection conjecture is true, we show that k-vertex subgraph counting is not solvable linear time for k greater than 5, even for bounded alpha. And to show this for any k, we need to exhibit one pattern with k vertices and say that, okay, this pattern is not countable linear time. And, okay, so so our strategy is to reduce from the triangle counting problem to the k cycle counting problem. So here I'll just I'll just explain to you the reduction from triangle counting to 6 cycle counting, but this could be easily generalized to larger cycles. So let G be the input graph of triangle counting. Just replace each edge with one new vertex, a red vertex, and connect it to both ends. And this way we construct G6. Notice that we have only doubled the number of edges, but now the arboricity of the graph, or the degeneracy of the graph, is at most 2. So, if we construct G6 this way, each triangle in G, you could easily see that translates to a 6 cycle in G6. And each 6 cycle in G6 has to be alternating between the vertices that were originally in G and the new vertices that we have added. And that translates to a triangle in G. So if you have an algorithm for counting 6 cycles, we have an algorithm for counting triangles. So this gives us the chasm at size 6. But we know that there are some 6 vertex or even larger patterns that are countable linear time. For example, Chiba and Ishizaki actually have m alpha to the k minus 2 algorithms for k click counting. And our algorithm is also able to count clicks and also many other patterns, like for example, here we have one. So we asked a more general question that assume bounded degeneracy. What are the characteristics of a pattern that actually makes it countable in linear time? Thank you.
All right, any questions? All right, if not, let's thank the speaker again. Siqi Liu telling us on the impossibility of probabilistic proofs in relativized worlds.
Thank you
for the introduction. So this is based on joint work with my advisor, Alessandro Chiesa. So at the very beginning, let's look at the historical reasons why people are studying relativization. Here by relativization, I actually mean complexity classes with oracles. So at the very beginning, people are hoping that by studying relativized complexity classes and how they are related to each other, we can infer how the unrelativized counterparts are related to each other. However, very famously, we know a counterexample, which is by Baker, Gill, and Solovy, that says that there exist two different oracles relative to which the relativized complexity classes P and NP have inconsistent relationships. So people revised this conjecture and now focus on the random oracle. The conjecture now becomes relative to the random oracle. The relationship between classes would be hopefully consistent with the unrelativized counterparts. And this turns out also to be false. And we know that in the unrelativized world, IP is equal to P space. However, relative to the random oracle, IP is not equal to P space. So from there on, people turn around and start to study relativization as a proof technique barrier. And this has been a fruitful direction. And ever since, people have found like stronger proof barriers, such as algebraization and natural proofs. But today, we'll be studying relativization with a completely different motivation. That is to understand the limitations on the efficiency of probabilistic proofs. So in the rest of the talk, I will first give a definition of probabilistic proofs, and then I'll use an example to illustrate this motivation. And finally, I will talk about our results. So probabilistic proofs, there are many different types of probabilistic proofs. I will use PCP proof system as an example. We recall that a PCP proof system for a language consists of a prover and a verifier. On input Y, the prover will produce a proof string, which the verifier probabilistically check at a couple locations, and then the verifier would output whether it accepts this instance or not. We have the requirement that if this input is inside the language, then the verifier should accept with high probability, and if it's not inside the language, no matter what the prover produces, the verifier should reject with high probability. So now we're going to look at example of language that arise in practice. So first we define script H, which is the class of hash functions, a family of hash functions. And then from here we can define the so-called hash chain language that consists of the tuple Sn and Xy, such that when you apply the hash function Hs to Xn times, you get the output Y. So if we're to construct PCP proof systems for this language using known techniques, what would happen is that efficiency of these PCPs would depend on n times the circuit size of the hash function. Because of this, a lot of work has been put into trying to optimize the circuit size of like primitives, like the hash functions, to improve the efficiency of the probabilistic proofs. But we ask the question that, is this optimizing circuit size necessary for us to do in order to improve the efficiency? The answer we have is that actually it depends on whether relative to the oracle H, the class P is contained in the class PCP. Let me explain what this means. So here we have the traditional we have the standard PCP proof systems for the hash chain language that we mentioned in the last slides. Wouldn't it be nice if we're able to construct a slightly different PCP proof system in which we give the prover and the verifier oracle access to the hash function, and now we slightly change the hash chain language to be a hash chain oracle language, which is a collection of language, L of S, and each of S only consists of N, X, and Y without the input S. Well, first it's unclear whether such a new oracle language admits a proof of this specific format. But it turns out that if relative to this hash function, P is contained in the class PCP, then our script L language will actually have a relativized PCP proof system. I will not really explain why that's the case, But we just need to know that if we can construct a relativized PCP proof system for the language L, then this PCP's efficiency measure is independent of the circuit size of the hash function. So that means in this case, it's not necessary for us to optimize the circuit size of the hash function in order to improve the efficiency of the PCP proof system. So we now are interested in the specific question whether relative to H, the class P is inside the class PCP. More precisely, we're actually asking for what kind of oracle is H. Does it hold that all the deterministic T-time oracle language can be verified by a relativized PCP in time little o of T? So to parse that question a little bit, it's asking if PCPs can compress deterministic computation in relativized worlds. So from here, there's also a natural question to ask whether when we are trying to improve the efficiency of PCP proof systems for non-deterministic language that involves like primitives, whether it's necessary for us to optimize the circuit size of these primitives. So it turns out the answer to this question is very similar to the answer for the deterministic language. It turns out that it all depends on whether relative to the primitive, NP is contained in PCP or not. So let's parse this question a little bit. It actually asks whether PCPs can compress witness size of non-deterministic computation in the relativized worlds. Okay, so now we have the questions in hand, and there are some prior works that give us like partial answers to these two questions, so we'll take a look at them first. So actually for now, prove that there exists some oracle A such that the non-deterministic computation, relative to this oracle A, the PCP verifier cannot compress the PCP proof system cannot compress the non-deterministic witness size. But this only tells us about one oracle, and this oracle is not a primitive that's commonly used in practice. And second, the Hardness et al. Actually proved that relative to the random oracle, the PCP verifier cannot compress the non-deterministic witness size by too much. But it doesn't rule out the probability, it doesn't rule out the case that it can still compress the witness size non-trivially. So these results are not quite complete or not quite strong. So we proceed to study this question in more detail. And here's our results. And also, they didn't tell us anything about deterministic computation. It's all about non-deterministic computation. Okay, so here's our results. We consider three specific oracles. The first is a very hard random oracle. And we're able to show that in this case, relative to the random oracle, a PCP proof system cannot compress non-deterministic computation's witness size. Neither can it compress the deterministic computation. So for the slightly more structured and well-studied well-studied oracle, generic group oracle, we're able to show the same results, similar results. And finally, for the even more structured low-degree polynomial oracle, we're able to show that relative to these oracles, the PCP proof system cannot compress non-deterministic witness non-trivially. However, for the deterministic computation, we're able to show that the PCP verifiers, the PCP proof system, cannot compress the deterministic computation a lot, but we still didn't rule out the probability that it could still compress the deterministic computation non-trivially relative to this low-degree polynomial oracle. Okay, so far, all these results are stated for PCP, but we know there are more probabilistic proof systems than just PCP. So actually, our results also extends to other proof systems like interactive oracle proofs, interactive PCP, and IP. Everything in the previous slides still holds for all these proof systems. And finally, I will conclude with some open questions. So here's the story so far. We have a spectrum of oracles. On the very right-hand side, we have very hard oracles, such as the random oracle, the generic group oracle, and also the low-degree polynomial oracle. And we're able to show that for these very random oracle, we have the PCP verifiers cannot compress deterministic or non-deterministic computation at all. And on the very left-hand side, we have very easy oracles, maybe like identity function or something. And the verifiers can very efficiently learn these oracles and then apply standard PCP techniques to construct a very efficient PCP proof systems or other probabilistic proof systems. So somewhere on this axis, the oracles turns from being easy to being hard. So the question we want to ask is, what are the precise criteria on the oracles under which suddenly the oracles become hard and does not have non-trivial relativized PCP verifiers? And also, it would be nice to be able to say something about like concrete cryptographic functions like pseudo-random function family, whether those oracles fall on the easy side or on the hard side. So, and that's it, and thank you.
Great. Any questions for Sichi? All right. If not, let's thank her and thank all the other speakers in this session.